Okay, welcome everybody. Today we have Xavier Lurton, specialist in underwater acoustics and longtime CCOM collaborator, speaking on calibration of echosounders and backscatter processing. Yep.
That's it. Well, good afternoon, everybody. Thank you for coming. Thank you, Lynette, for the invitation. And well, I'm presenting today a number of recent achievements and results obtained by our team at the Underwater Acoustics Laboratory at Ifremer. Obviously, that's a teamwork, and so we'll have contributions by people that you may know or may not know. Jean-Marie, Laurent, Dimitrios, Rida, Luciano, and Naig. So I will briefly introduce the context and expectations about Seafloor Backscatter today. Then we'll address first topic that's about backscatter measured by Multibeam Echosounders and how to calibrate the sensors, and concentrating on two particular methods, that's the method of the reference areas and the method of cross-calibration between systems. Then I present the results of an interesting case study based on the exploitation of a large-scale data set obtained with a calibrated echosounder. Presents the system itself, the survey characteristics, and of course the results. And I conclude with some takeaways that you will be able to meditate on during the weekend. There is today an increasing interest in the use of Seafloor Backscatter measured by sonars. The applications, as you know, are many, from science to environment to hydrography to naval applications. For instance, you can find mention of this, the use of backscatter, in the directives of the European Union Marine Strategy Framework. And rumors are that in the upcoming IHO recommendations, more about the backscatter could be mentioned as well. This corresponds to ongoing fast improvements in the technology of multi-beam systems. These sensors are gaining in resolution, in accuracy, in dynamics of the signals. Now they are reaching multi-frequency capabilities, which open new fields. And calibration methods for backscatter, are being developed today, together with the development of dedicated software tools. So today, there is indeed significant activity in the field. A number of research projects with leading groups that I will tell a word about. And which is new, an increase of the support by heavyweight end users like NOAA in the US or SHOM. SHOM is a national hydrography service of the French Navy in France. Such operators are more and more interested by mapping backscatter. A few years ago, we have launched in the framework of the GeoHub community, that's a scientific community organized around the topic of habitat mapping. We have launched a working group all dedicated to the measurement and the processing of Seafloor Backscatter. Today it gathers about 300 people, a number of them are here, by the way. And the working group, which I chair together with Geoffroy Lamarche from NIWA, New Zealand, we have produced 3 years ago a first report that's guidelines and recommendations for users of backscatter, and coordinated a special issue on Seafloor Backscatter published in the Journal of Marine Geophysical Research. A word about the fundamentals of the methods that we are using for backscatter processing in our team, I mean. For us, the main observable, the physical quantity we use is the backscatter strength, absolute values. This implies some sort of calibration of the sensors, and exploited versus the angle of incidence. Okay, that will be the BS zeta in the following. For in all the following, BS will be for backscatter strength. And so once the backscatter strength is measured, it can be fitted to a heuristical model that I've proposed a few years ago, which is not really a physical one, but rather a descriptive one. The shape of the angular dependence of the backscatter strength is described by a small number between 4 and 6, a small number of parameters which can in turn be associated to physical characteristics, but which may be as well taken of dimensionless things describing the general shape of this behavior. Yes, these can be extracted from the fitting of the model, and the segmentation of the backscatter maps are made according to this acoustical response. Also, we privilegiate ground truthing rather than model inversion for associating the backscatter response to the seafloor characteristics. An example of such experimental results is obtained during a series of surveys in the English Channel, 13 surveys on limited size boxes, from which average backscatter strength versus angle can be derived and can then be associated to the results of ground truthing, which is obtained either by sediment sampling or maybe more interesting by taking video films close to the seafloor. Okay, that's for the fundamentals of our approach. This to illustrate the urgent need for references. That's the first example, which gathers as a mosaic a number of historical data from CHS. Well, it's a bit cheated because the sensors presented in this mosaic are quite different from one another. The frequencies are different. Maybe this one is more dramatic. This is taken in New Zealand by one ship and one echosounder. Well, it's along the years, obviously, so the sensor may have evolved. Nevertheless, well, this is scary. So today, the need for calibration may differ according to the applications and what are the objectives that we should try to reach. Basically, you have two types of applications for seafloor mapping. From this point of view, it's either exploration or monitoring. Exploration is mapping of new areas, try to classify, to identify, to characterize, to model the response. For this, you need absolute values of the backscatter strength. It means that you have to compensate for everything in the sounder, its directivity, the gains, the source level, everything. Now, if you are rather on the monitoring side, then you want to monitor known areas and you are interested in variations. And so in this case, you may be happy with relative levels, provided that your data are consistent with time. So it means that you have some sort of calibration, of relative calibration to ensure anyway. Sensor biases are tolerable, which was not the case for absolute backscatter, but again, if they stay stable. A good quantified objective could be a magnitude of the uncertainty of plus minus 1 dB. Well, frankly speaking, this is not really reached today, but this is a good objective, since it should be acceptable by users. It is reasonably obtainable by engineers, and as well operationally by the operators. So I am now addressing the calibration methods that you can imagine for backscatter measured by multi-beam systems. The first one, which is the very basic one and very difficult one, it's what I'd call the metrological approach, meaning you dip the system in a tank or whatever, and you measure directly all its electroacoustical characteristics. That's a very heavy work to conduct, because there are many things to measure, and that's quite tricky. Here at CCOM, there has been a number of works conducted in this direction by Carlo, Tom, and other colleagues. So this is obviously reserved to very well specialized and well equipped teams and labs, or to the constructors. Not any user of multi-beam can imagine this. The second approach, which is quite derived from the fishery acoustics world, that's working on a reference target. The reference target is invariably a small metal sphere with very particular characteristics according to frequency and so on, which is deployed under the echosounder and used to measuring the echoes from the metal sphere, to measure the response of the system and its directivity. So this is an old method. It has been used for decades with single beam echosounders in fisheries, and it has been proposed to apply it to multi-beam as well. This raises a number of operational, practical problems when applying it. Then you can use natural reference seafloor areas. These are places where you know in advance exactly what the seafloor response will be. So your sensor is then placed in survey conditions, which is good. And so you directly compare what the multi-beam measures with what it should be, what the local physical reality is. The difficulty here is to get and to identify and to qualify these reference areas. That's difficult, possible still. And here, Tom and colleagues have worked on a reference area close to here. And I will present you in the following what we have done on our side. And finally, a second method I will present then is what I call cross-calibration. That's you compare, you adjust the data of your system to calibrate with an existing one, which is already calibrated. Normally, you can do it absolutely anywhere. You don't need a specific area for this. However, it's better to do it in a controlled environment. Before addressing the issue of underwater reference areas, we make a small detour by the space and see how things are going with satellite radars. Satellite radars, I mean here scatterometers. They are not exactly the famous synthetic aperture systems. They are much simpler ones aimed at measuring really the backscatter. They are designed for this and only this. And they work quite like side-scan sonar, actually. That's a very similar geometry. So very simple systems with a lot of interesting applications with surveillance of the sea surface without or with ice, the soil moisture, the vegetation, agriculture, a lot of things. And the community of users are quite demanding for all these applications. And they ask for half a dB, possibly 1 dB. This implies that the sensors have to be periodically checked. And of course, with this type of installation, there's no way to start interventions directly on the instrument, obviously, so everything has to be done in flight. This is, I do like this image. They're wonderful. That's the backscatter strength of the Earth, the average value for the upper plot, and its standard deviation over the year on the lowest one. From this, satellite users, they identified a very interesting region, that's the Amazonian forest in Brazil. And for years, for decades now, they have been using it as the absolute calibration level for the satellite radars. Because the forest canopy provides a high reflectivity level, it's isotropic versus angle because of the very shape of it. It's extremely stable over the year. There are small variations due to seasons, but they are under control. And so no one could find a better reference area ever since. So it's still used today. So the challenge for us now is, since we cannot install the multibeam on satellites, is to find the equivalent of an Amazonian forest underwater. Calibrating a backscatter on reference areas raises a high number of advantages. Imagine, the multibeam is operated in its operational configuration, so the echoes and the targets, they are real things, not this artificial metal sphere. The calibration operation and the survey operations are the same. So this can be conducted very efficiently. And more than that, you can imagine to combine this with the other calibration operations that are made routinely for the bathymetry. Again, the big issue is how to define and to qualify the reference areas. So there's a number of criteria of acceptability, and one must also determine the absolute levels, which will be the reference data, and of course, be ready to detect possible changes in the characteristics. So what are the requirements for this? The keyword is predictability, obviously. You want to know in advance what the backscatter will be. So to make things easier, you will favor a quite flat area with a significant extent so that you are able to calibrate multi-beam with a wide aperture. It's better to have high reflectivity levels because your signal to noise ratio will be better as well, and to have an homogeneous area for obvious reasons. It has to be stable with time as far as possible, and to be as isotropic angularly as possible, both in the vertical and the horizontal plane. Ideal areas fulfilling these requirements, they are seafloor with a rough interface or much volume scattering. Like this was the case for the Amazonian forest. So starting from these requirements, we have surveyed and checked a number of possible areas around Brest. And well, the idea was to concentrate on places that we already knew because of science studies or because of hydrographic habits of shrimp, for instance, around the Brest Harbor. So we have series of historical data that are available, which is good to check the stability. And we have so conducted these survey operations. And the only one that I will present, which is the best one, is named the Carré Renard. That's a shallow area, about 20-meter depth, covered with coarse and even very coarse sediments. You can see on the video still frames here. That's very close to Brest Harbor. Actually, it used to be a reference area for SHOM, for calibrating the hydrographic launches, because it's very convenient. In 10 minutes, they are on the area. And the area is bathymetry-wise very stable. Nevertheless, we surveyed the other one very seriously, but the other 6 ones were found either unstable or heterogeneous or anisotropic. So finally, the only one, the reference area, finally, is Carré Renard. Actually, and more recently, we tried to find another one because Carré Renard is 20 meters deep. And so it's okay for high frequency systems, let's say above 100 kilohertz. For lower frequency, it's a bit annoying. And we identified an area here close to the famous ocean island, l'île d'Ouessant. An area with 200 meter depth, which is very rare there, and a nice flat coarse seafloor, and a number of inconveniences. That's at least 2 hours from Brest. It's not sheltered at all, and so usually the weather conditions are quite bad. So this one is still upon validation, but we have started to use it recently this year. An illustration of the interest of this method of reference areas, you can propagate the calibration of a system or an area to other places. For instance, we had a few years ago an interesting cruise over 3 different reference areas. So it all starts with, again, Carré Renard, which is characterized by our local oceanographic vessel. A second vessel, Belgica, stops in Brest and surveys Carré Renard. Belgica is equipped with an EM-3002, and since Carré Renard reflectivity has been calibrated, the Echosounder of Belgica is calibrated as well. Then Belgica sails back home and surveys the Quintebank area where the Belgians have their reference area. And so since the Echosounder is calibrated, Quintebank is calibrated in turn without going for the intermediate operations that we have conducted in the Bay of Brest. And then another Belgian vessel can survey the same area, and he can calibrate the EM-2040 in turns. Something very interesting that we have observed when qualifying our reference areas is the angle dependence of the backscatter in the horizontal plane. We systematically run survey lines at a variety of heading angles, azimuth angles, and normally on a good homogeneous seafloor, you get this type of things. Whatever the direction that the ship is sailing, you have more or less the same thing. You can plot nice polar directivities. This one was recorded on the famous Carré Renard. That's a very rough seafloor, so there's some noise on the data, but basically no dependence on the azimuth. Now, the same ship surveys another area close to Brest, where instead of coarse material, the seafloor is rippled sand. And that's the result. According to the direction of the survey line, you see that each backscatter line is quite different. And when you average the angular response for the various directions, you get this type of things. With, in this case, a maximum dynamics between the azimuth lines of 7 dB.
Is that the average for all the things moving across?
Yes. The area is homogeneous enough, and so each one of these curves is all the pinks stacked, averaged. Even more scary. This one was measured on another supposed reference area, Les Pierres Noires, that's outside the Bay of Brest, 60-meter depth. And this used to be, this still uses to be a SHOM reference area for bathymetry. We went there in June 2014, and we got this. Very nice results. So, well, we thought that Pierre Noire would reasonably become a backscatter reference area as well, since it was already a bathymetry one. It was perfect. 1 year later, at the same place, with the same ship and the same sonar, we get this. Here, you see that the dynamics is up to 12 dB. That's marvelous. Obviously, this has to do with the seasonal tides and currents. We don't know today which time scale is concerned by such changes. It may be seasons, it may be as well hours, maybe inside inside the tide cycle this could happen, we don't know. That's it. So some conclusions about this azimuth dependence. Obviously, it strongly modifies the backscatter response, and so the resulting backscatter map. Well, I don't present this, but you can model it quite conveniently and really understand what's happening. This issue is especially problematic when you cannot detect the ripples on the sonar data. In some cases, you have these big sediment waves. You can see them easily on the sonar images. You can even see them on the bathymetry data. Even here, it's not the case. We are with current ripples, sediment ripples, that are typically 10 to 20 centimeters of wavelength. Not enough to be resolved by multi-beam systems. Well, the bright thing could be that you could use such measurements to detect the presence and the direction of ripple fields. The time dependence I have mentioned. So at the conclusion, it's highly undesirable that you use areas with such phenomena for your reference areas. Now, cross-calibration method. The basic principle is that you deploy on the same ship for as far as possible joint recording. Well, you could postpone it, but it's better to have it at the same time. The multi-beam to be calibrated, and a reference system that could be another multi-beam, but for today we use only single beam calibrated system. This reference system, it has to be at the same frequency as the system to be calibrated. It has to feature a similar aperture, pulse durations, and it has to be tilted and accurately positioned because you want to access to the angular response. So the constraints to the method is that you have to calibrate first the single beam. You have to install on board some dedicated equipment to be able to measure accurately the tilt of the single beam. And maybe the biggest constraint is that it leads you to quite long time surveying, because for each line on the reference area, you can measure only one angle and one frequency with a single. So well, you have to plan cruises with very long time and a very passionate crew on board. Yeah. Because you are surveying again and again and again the same way. So that's the experimental setups that we used. So our coastal vessel, Thalia, with her brand new or so EM-2040 dual. And on the side, a pole equipped with a single beam system. So this was the first installation. So it was all mechanic with one single beam transducer. And to change the angle, you have to raise the perch again, dismount everything, change the angle, and do it again. So we have improved the system, and now instead of this, we use a pan and tilt system, which is controlled from the ship, and so you can scan at any angle and without taking the pole on board again. Also, we can install several single beam heads on the same plate. And well, that's an example of a result, cross-calibration on carré renard with an EK60 Simrad system, 200 kilohertz, and our 2040 EM-2040 working also at 200 kilohertz. And that's the result, and that's not so bad. The single beam data are in green, and the dark line is the multi-beam. And this gives us this calibration curve that we can then apply to the 2040 data. So you see it's not perfectly, but quite aligned on zero, meaning that the average measured levels given by the constructor were okay. And the fluctuations around this are, well, in the plus minus 1.5. Okay, and this you have to do again and again and again because you want to do it for all the frequencies of the multi-beam, if it is multi-frequency one, that's the case, and all the various modes, shallow, deep, and so on. That's it. So we are in the middle of it. We are quite fairly advanced for the frequency range corresponding to the 2040, meaning 200, 300, 400 kilohertz. And now we're getting to lower frequencies. So we have started a series of surveys in the mid-frequency range, 120, 70 kilohertz. So this will make us able to calibrate systems EM710. And even more recently, we used the 38 actually, Echosounder in order to calibrate our brand new EM304 installed on Thalassa since September. And so we are in the position now to cross-calibrate in this frequency range. What I don't know is what we'll be able to do with this frequency range. If we want to go down to really deep water, low frequency systems, I can hardly imagine that the same methodology could be applicable because calibrated single beams at 12 kilohertz that you can tilt, well, it's not an easy concept. Interestingly, thanks to the progress in the instruments, we are able now to collect the response of the continuous data set versus angle and versus frequency. And this is thanks to these new wideband single beam echosounders, Simrad EK80, which make possible to cover completely the complete frequency range. Actually, we are able to do it from 45 to 450 kilohertz. And so we have recorded the first series of data covering this frequency range by third of octaves. It's a lot of data because it is in the same time varying with angle from 0 to 70. That's a lot. And well, the work is in progress, and Luciano, that some of you know well, he is now on a sabbatical with our team, and his mission is to take care of this multi-frequency, multi-angle data. And to finish, I'll present the results of a case study that has been conducted by my two colleagues, Laurent and Rida, using quite a special multi-beam echosounder, that's ME70, not by Kongsberg, but by Simrad, and that's a fisheries multi-beam system. So it has been developed about 20 years ago, and today It's quite a reference actually for fisheries acoustics. It's installed on 2 Ifremer vessels, on half a dozen of NOAA vessels, about the same number at IMR, which is the Norwegian Fisheries Institute. NIWA has bought some as well. But that's a nice scientific tool. But it's a fishery system. So we had it evolve by buying from Kongsberg Maritime, so the bathymetry company in Kongsberg, a specific module or option which adapts to the fisheries ME70 and who makes possible to use this ME70 like a bathymetry system. So using the same operating system, SIS, with quite modest, actually, performances as a survey multi-beam. Quite wide beams, not so many soundings, but that's okay. And the very good thing is that it can be calibrated directly, the way fisheries echosounders are. This system is used in a number of scientific programs by Ifremer, and especially in this so-called EVOE program that is designed for long-term monitoring of regional area between Ireland, France, and Spain in the Gulf of Biscay, both for fish stock assessment and for habitat mapping. And so this program has lasted for about 10 years now, and it's all on the same ship and it's all with the same system. So that's fantastic because, moreover, the system is calibrated. The seafloor mapping data, they have been kept carefully in Ifremer vaults for 10 years, and suddenly their owners discovered that maybe it could interest us to process them, and we said, yes, it should work. And so only last year could we process this data. The shortcoming of this data set is that there is very little ground truthing available. That's a pity, really. So that's it. That's the geographical extent of these cruises. Okay, we are here, and the playground goes from Ireland to the Spanish frontier here. So it's all over the continental shelf of the Bay of Biscay. The acquisition methodology is very strict. For each one of the 160 or so boxes, so-called boxes, it's all around one main trawling line. Don't forget, it's all about fisheries here. One trawling line, which is trawled during the daytime, and at night, it's surveyed. So with this data, what do? We first compute the bathymetry of the area, the corresponding incidence angle, correct them from the topography, then we get the backscatter versus angle curves. Then we can segment the data for each box into a small number of homogeneous seafloor types. Then we average over the area and we fit the heuristical model on this. Then we extend it at the global scale of the region, and we can then classify the acoustic response at a regional scale and build the map. So in more details, that's on one box, so a few kilometers wide, the geographical mosaic, then the data presented as piled up pings versus incidence angle, And the idea here is to just take crosscuts here at a given angle and look at the distribution of the amplitudes. If you cut this guy there at 35 degrees, you got this histogram here, which is clearly bimodal, which is not unexpected considering the mosaics. You do it for other angles, it works as well. So finally, you identify the two modes of the distributions as two different seafloor types. And then your data becomes this yellow and blue map that you can geographically reference again. And you can take the average response of all the points on the area according to the two types. We do this for all the 200 and so surveys over 160 different areas. And we get with this about 400 angular curves that we then classify into 12 classes. This is arbitrary. Could have been less or more, but well, it sounded to be a good number. These are the average responses corresponding to these 12 classes. Now we affect the observed classified seafloor. We affect these seafloor types to all the boxes, and that's it. With obviously a nice consistency, a nice geographical consistency of the seafloor types according to the place. Zoom on it. And the good thing is that during the transit lines between the boxes, the sounder was still on. So we have a lot of data that interconnect all these points. So we have not conducted such a fancy, sophisticated processing as we did with the boxes themselves, meaning that we have not as carefully corrected for the incidence angles due to the topography. It's more simple than that. Nevertheless, we conduct, with this simplification, we conduct the same processing, the same classification, and here we are. So finally, we mixed this with the results from the boxes themselves, with some extrapolation and smoothing around it. And here we are. That's what we can get from this data set over the Gulf of Biscay. A zoom on the Brittany Cape. From this, you can extract various byproducts. Here I have plotted the backscatter at 45 degrees, for instance. Can do a lot of things. So to conclude about this approach, it's, let's say, promising and interesting because you can work with the data both at the local scale, the boxes, or at the regional scale. The detection of classes is quite simple, very simple actually. And so the computation load is quite light. So this is a good proof of concept of this method. We have to admit that this is a remarkable data set. And so it was bound to work. Because, well, one same calibrated sensor for 10 years, well, this is not something very common. What's important also is that the acquisition protocol was very, very well controlled. And believe it or not, the scientific community, I mean the geoscience, they showed interest in the results, which is not so often. And now they all want to have this type of surveys to complement their cruises. So now we are required to design upcoming cruises with the same protocol, even from other programs than the original ones. That's fantastic. And but now we'll be demanding, and we ask for ground truthing operations systematically, because once again, this is lacking in our present results. We classify in 12 acoustical responses, and that's fine, but it should be better to affect it to actual Seafloor types. And some takeaways. I'm sorry, I'm a bit long. General things: the mean backscatter, a powerful descriptor at the regional scale. I think you are convinced of it. Okay, high resolution systems are not necessary. That's obvious because of the scale. Multi-frequency could offer a new potential. Well, we are still in the process, and we are not alone actually. So some of you guys are also in the field. This may be really a new direction to investigate. Calibration is fundamental, or at least ensure the consistency between the data. So the community needs more calibration tools and more results. A few recommendations to constructors. Today, well, the status of the multi-beam systems regarding what we know about backscatter on the seafloor today, well, there's not a good match today. So they should really improve the functionalities of current systems and guarantee that the new systems are delivered with some standard of backscatter measurement accuracy. This is not the case today. You have to ask specifically for it, and it looks like they do you a favor in providing a calibrated instrument. This should not be the case. On the other hand, the users community should go further in defining reference areas, getting well-controlled data, including the ground truthing, and disseminate them. And this should be a common effort, I think, especially regarding the deep water areas, because for shallow waters, you understand that each team can do it more or less on its side. This happens, you do it, we do it, okay? For deep waters, high sea vessels, and so on, low frequency systems, this is something else. And finally, recommendations to users and operators, maybe you guys. When you design your survey cruises, take into account the backscatter requirements as well. Today, it's all about bathymetry, while getting good backscatter implies particular precautions. When you buy a new multi-beam, well, this happens, insist on the constructors so that they conduct calibration operations from the factory acceptance test. And then, during the system life cycle, think of recalibrating it. It may be good also to follow the training provided by the software vendors regarding backscatter, because this is a difficult thing and much more difficult to automatize than the bathymetry processing. If you map for monitoring, a strange piece of advice is do not change your system. Keep it as long as it works and don't listen to the vendors. Because you will be disappointed when you will change your system. So in short, you should read and follow all the backscatter working group recommendations. All of this is written in this report, so I encourage users to download it and to read it. And that's it. I've been a bit lengthy, sorry. Thank you for listening to me, and if you have any questions, I'll be glad to answer.
Yes, I'm not quite clear on the disadvantage of the metal sphere versus. Why do you need to let them tell you it's a metal sphere?
For practical reasons, for mainly geometrical reasons. One of these is that multi-beam echosounders have these very big arrays, or not so big, but large compared to the wavelengths, meaning that the far field limit must be huge. Actually, for low frequency systems, it may be hundreds of meters. So you have to send this target there. Then the target sphere method, it works well because fisheries echosounders, they are so-called split beam systems, meaning that they can make interferometry between parts of the array. And so they can localize very accurately the target inside the horizontal plane. With multi-beam systems, you could imagine this across track, where there is interferometry indeed, but along track, there is not. So you have a problem as well with the positioning of the target. And another disadvantage is the geometry of the system, which may shoot at 75 degrees on the side. And then how do you send your target so far? This is completely yes. So it's not unfeasible, but it raises a number of constraints. Especially when you think of a ship-mounted system. If you have a small high-frequency one that you test in the tank, yes, this is much more practical.
I was surprised to hear you say that when you're comparing your EK to the EM, that you want the same pulse length and the same aperture. You really can't get the same aperture. Anyway.
No, aperture you cannot. So you have to do with it and do the corrections that are needed for this. And for the pulse length, you do what you can.
I mean, ideally, it shouldn't be pulse length, correct? It shouldn't be necessary to match the pulse.
I agree with this. Yeah.
Just curious.
Yes, because there are always surprises with this. For instance, well, it's not a secret anymore, but we have discovered that the pulse length that was announced in the Kongsberg runtime parameters, they were not quite the actual physical ones. There was, due to the definition of the pulse length, was it the total, because they are shaded waveforms. So according to the definition, there was an ambiguity, and the actual pulse length was not the nominal one that we used initially for compensation. So we were in error by up to 2 dBs. That's a lot. Due to this. So we decided now that we should limit the risks linked to pulse length to a minimum. But you are right that ideally it should not be a problem.
So your last two recommendations, I confess that I haven't read the backscatter working recommendations. But the one before that,
you should then.
I will, promise. The one before that is a real problem, I think. So if we run a multi-beam for a decade, we're going to, depending on who our regulatory agency is, we're going to be in the shipyard 5 times or 3 times and mess around under the ship. I'm not aware of any of modern multi-beams that will run 10 years without some component changes.
Yes. No. So the idea is this is obviously something that has to be done.
Unless you lock up the computers.
But you have to be conscious that waste exists, and the solution may be recalibrating again after every heavy operation.
Or once a year or something. So the question is, how do we arrive at a practical recalibration method?
I gave a few solutions. Reference areas can be one. Yes.
But I think that's a really important sort of operational piece. Mm-hmm. When we schedule ships per year,
Yes, but the funny thing is that calibrating for bathymetry, no one has any problem about this. That's normal.
Normal in some operations, but not as normal as you would like in others.
Oh, okay.
So I think we as a bigger community need to put some emphasis on that, so ship schedulers and operators allow that time to be in the schedule.
Hmm.
You work on your negotiating tactics. If you start,
I'm well known for my negotiating.
You want to drive the ship to the Amazon rainforest, calibrate the backscatter. You're missing the pattern. You got to take a ship to the Oh,
that was in the first line.
No, but maybe there's some pedagogy to go on with the scientific users. It's not unreasonable for a scientist when he goes for a field data acquisition that his sensor is calibrated and that he accepts to spend some time calibrating his tool. In many domains of physics or any experimental science, people find it normal to calibrate the sensors.
I think we have to bring this normal to the people in that report.
I was just curious, which algorithm did you use to cluster the data set into 12 different classes?
Okay, then I will send you to my two colleagues who will be very pleased to answer you in details. And this avoids me to tell you silly things.
Yeah. You have to know the calibration for each frequency. You just do the reference area or the cross calibration. You have to keep the system with a wide range of frequency. You have to run them.
Well, it depends on your needs. Actually, if you just need to calibrate one simple system working at one frequency, just concentrate on this one. What we are doing here is to investigate quite systematically as many frequencies and angles as we can. So to be able to calibrate various systems and knowing in advance what should be the response.
And the result of the calibration is a curve, right? The decimal curve.
Yes.
How do you apply that?
Oh, that's in the ideally, this should be taken into account by the constructors, who should provide some way to inject this inside the multi-beam processing modules to correct in real time. Not yet the case. So you have to do it in post-processing, and when mosaicing your backscatter data, for instance, apply this systematically. I think the software vendors today, they propose such options in the toolkit that they sell you. In post-processing, yes, and hopefully someday in real time.
Any more questions?
Thank you again.